Welcome to the Let's Build a Drone webinar. This is our second webinar about building a drone. This is a drone project. It's a great way to introduce design as a opening into the 3D modeling course, which will teach them a lot. It's quite a bit of fun as well. So my name is Sheila. I do want to acknowledge that this webinar series is made possible by a Nevada State Library, Archives, and Public Records Continuing Education grant funded by the Institute for Museum and Library Services through the Library Services and Technology Act. Many thanks for that. For those of you who aren't familiar with NCLab, what we do is we provide a self-contained desktop platform where you can learn and use computer programming, modeling, and many other STEM skills. You learn through self-paced, self-graded courses. This is great because anyone can sign on and start learning. You then can apply the skills you learn using the apps in Creative Suite. And today we're going to talk about an Hour of Code tutorial. We have two at the moment. One is for Carol, and this one introduces people to 3D modeling by building a drone. If you would like to follow along, you can go to hoc.nclab.com/3D/ and follow along. Or you can sit back and relax and watch me do it today. All right. I'm going to explain why we chose drones very briefly, and then I'm going to go through the 10-step tutorial. This is the Hour of Code tutorial. Then we'll go through the steps of actually building and flying the resulting drone. Take a look at some projects that you can do with it, how you can link it to real-world skills. And then in the wrap-up, I do have a suggestion for a camp or a club, which is multiple sessions. And then we'll take some questions and answers. So drones, what's the big deal about drones? Well, they're nothing short of a revolution in just about any field you can imagine. If robotics is important, then drones are robotics with the advantage of flying. They're used in data collection, they're used in delivery systems, they can be used in hazardous environments, including deep ocean and space. So you think of flying drones, but we also have underwater vehicles that explore deep oceans. I was very fortunate to be involved with a project last year where they're using underwater drones in Antarctica. Very interesting stuff. And they've also been exploring deep ocean trenches where there's no way you can even send a manned vehicle of any kind because of the pressures, but they're discovering just some amazing things in the deep ocean. And of course, you can send them into outer space. They don't need what we soft-bodied organisms need to survive. They can be used through manual operations, which we will be doing in this project, and they can also be programmed. And our next drone project will be programmable. And they're just plain fun. I have friends who race them up to 140 miles per hour, pretty amazing. They can be used for stunts, and a lot of people use them for photography. You get some fantastic viewpoints from drones. So together with the tutorial, we also have a set of lesson plans, and I'm going to toggle back and forth to those to show you what materials are available. These will all be posted on community. So anything I show you today, we will upload to the community shortly. Just to look at the lesson plans briefly, these are pretty detailed. There's a course description. There's the usual stuff on objectives and background, what you need for supplies to get started, some tips for success with students. We reference the standards, both the computer standards and academic standards. There's a 1-hour lesson plan, so this is for just if you want to run the tutorial itself. we explore some essential questions, and I'll go into those a bit more later. There's a page showing the layout and a little bit on the screen controls. And then there are detailed notes on each step. I'm not going to go through those today, but if you want to understand the geometry or an explanation of the keywords and the parameters, they're all in here. So this is all available for each of the 10 steps in the tutorial. Then at the end, there are some discussion questions, and there's also a worksheet that students or participants can use as a guide for note-taking and for reflecting on what they've just done. And there's an invitation to the project gallery, so if they want to see what people have built using 3D modeling, using the app, they can go visit that. There's links for the file that can be printed, and there are ways to personalize their own drone frame with their initials. And then we have a list of resources. So I'm going to just go through this really quickly, and we don't need to come back to it later. This is a note taker. It's 2 pages, which gives them space to write in some questions or anything they learned from each of the steps. Sometimes note takers are a good idea. What we have found, we've observed this, is that people get click happy. They want to click through whatever they're looking at on the internet, or in this case, a lesson, and they're not really engaging with it. So a note taker is a way of slowing down, and then if something's not clear, this is a place also to write questions. This is an exit ticket or a reflection. Exit tickets are commonly used in classrooms, but they can certainly be used in a club or a camp setting as well. And then there are some printable posters. So there's a poster on why learn 3D modeling. There's a poster on scripted CAD, and I'll talk about this a little bit more later. And then there's a poster on drones. So these are all printable, and you can put them up and stimulate some discussion, hopefully. Okay, back to the slideshow. So we're really looking at some key concepts here in computer science. If you need to justify your existence, here it is. One of the biggest problems when anyone starts coding is it becomes overwhelming pretty quickly. And that's because they're trying to solve too many parts of a problem at once. So a key skill in any kind of coding is to break a larger problem into a logical series of small, manageable steps. And this logical series part is important because you may need to achieve a certain piece first before you go on to the next step. Another key concept is the idea of parameters. And parameters are basically telling the program exactly how you want it to build a certain function. The nice thing about 3D modeling is this is very tangible. So for instance, if you're building a cylinder, you're going to tell it the radius and the height. Those are parameters, and you can change them. You don't have to dig deep into the program to see how it builds that cylinder, but you do need to tell it those particular parameters in order for it to respond to your needs. So we're really developing that idea of parameters. And then the third leg of this is that we're building a prototype. So this is not a gorgeous final design. This is a beginning step. It's a prototype. It begs a lot of questions. How could we make this bigger? How could we make it stronger? How could we make it thinner? How could we make it accommodate a certain process? How can we make it safer, and so forth? And we're really trying to stimulate that, the design process. For 3D modeling itself, we are developing something beyond computer programming. We're developing visual spatial reasoning, which in the old days when people were outside and doing stuff and working on cars or sewing dresses or whatever, that tended to come more naturally. We knew how pieces went together, and we don't have that as much these days. So this is one way to develop visual spatial reasoning. We're also using scripted CAD, and by writing out the code that tells how to build an object, students are learning something about the underlying math. So when they go to an advanced menu-driven CAD program, there are many out there that are used in industry, Autodesk, SolidWorks, and so forth. They understand what they're looking at. We're also applying it. Again, this is a real working model that flies in 3D space. So we're getting that reinforcement of visual spatial reasoning because we're going to learn a little bit about how flight works in 3D space. So each step includes tutorial pages before the activity. One trick when you're working with both younger people and adults, and we've talked about this before, is this idea of working in pairs. You have one person at the keyboard and the mouse, that's the pilot, and sometimes people refer to this as the driver. And then you have one person reading the instructions and giving some directions, and that's the navigator. And then they can switch. This is makes it a much richer experience. They need to know where to type the code, be familiar with the controls, and then there's a little trick here. If they run the pre-written code first before they make the changes, then they'll understand much better what's going on. So I'm going to go to the Hour of Code application. This is how it comes up. Press the red button to start. And there's my grid. And you can see that it knows I've already been in here, that I have a continue button, but I'm just going to go to this first one again. So it'll start out by explaining what they're going to learn in the tutorial. Let that load here. And then just a little encouragement and explaining this first assembly that we're going to build. Now, you remember I said something about breaking a problem into components. This is a good example. This is a rotor duct, and we're going to break it into these three parts. We're going to build a rotor socket, and then a spar that holds the socket onto a rotor ring, which is the outer piece here. It explains something about scripting CAD, and then this is a screen that's important. This is the upper left-hand corner explains what to do. The lower left corner is where they type the code, and this can be enlarged. You can see it a lot better when I enlarge it. And then on the right-hand side, we have a viewer that will show what happens when we run the code. It's not showing the controls for some reason. Okay. I'm just going to go back into it. Aha, there we go. Now things are working. So, you know, this was always the first two steps in the IBM troubleshooting manual. You can pull the plug and start over again, and that's exactly what I had to do. Okay, now I can see the controls at the bottom. I'm not sure why they disappeared on me, but they did. But you know what? This is real life, and you may encounter that, and as you can see, that solved the problem. We have our controls back. Okay, so here's the code, and this first component, the socket that holds the motors, is formed by making an arc. So if I run what the existing code is, let's take a look here. Okay, you can see that it's an arc. I'm going to increase the size there so you can see it better. And the arc is composed of an inner radius. You can see this is 10 units here. So there's the inner radius going out to 10. And then 15, there's the outer radius. It's halfway between 10 and 20. And the arc itself has a turn angle of 90 degrees. So it's telling me now in the instructions up above that I'm going to make that inner radius 2.95. And my outer radius is going to be 4.95. And my turn angle is going to be 340 degrees. This inner radius is an important number to remember. What we've found is that, and this is if you go to use your own 3D printer, some materials are not very precise when they print. And you may have to increase this number a little bit to make those motors go into that holder, into the socket. I experimented with some PLA and I ended up using a value of 3.15 and it worked. Now you're not going to type it in at this part. You do get the entire code later on and it can be adjusted there. For now we're going to keep it at 2.95 because that's what's going to pass the level. And I'm going to run the code. And there it is. And you can see it looks quite different now. So this is almost a full circle and there's a small opening. When you put the motor in there, it'll fit very tightly. The motor is a 6mm motor. So the radius is 3 millimeters and this acts a bit like a spring. You push it in and then it'll hold it nice and snug. So once the code looks like what it's supposed to look like, and there's a little drawing up here that they can compare to, yeah, that looks good, then they're going to hit the submit button. And that's when it gets graded. And there's my grading box. It says I passed, no fails. So when I submitted it, it was correct the first time, and that gave me a score of 30 points. The points are really there just to encourage the students. It's not, let me scroll back down. It's not meant to penalize them, but if they work out all the bugs before they hit submit, then they're going to get a no fail pass. And then it'll go on to the next step. I'm not going to continue through the tutorial. I'm going to go back to the slideshow, but that gives you an idea of how each of the steps works, and you may want to go through that first step as a group. So this is what we just did. There's the pre-code, and again, encourage them to run that first and then change the values to see how those parametric values make a difference to the end result. In step 2, this is where we build the rotor ring. And again, there's some default code. It can be changed. And to the right, I put some ideas on what can be discussed out of this. The geometry of rings. Again, this is inner radius and outer radius. What we're doing here in the 3D modeling is known as object-oriented programming, OOP. And we create objects and then we act on them. So for instance, if I create an object whose name is RR, then I do things to the object. So I'm giving it a color and I'm using the show command to display it. Then you can also ask design function questions. What does the ring do? Well, what it does is it protects the blades, the propellers. It also protects you from the propellers to some extent. Step 3, we're going to put in a spar that joins the ring and the socket. And this is a good level to step through. I'm going to actually go quickly through to that, and then after that I will leave the 3D modeling app. I'm just going to get that real quick. Okay, so this was 19 and 21. Because I want to get through the next one. All right, I'm going to enlarge this here, and I'm going to show you this, the value of the step function. So you have the run arrow right here, but next to it we have a step function, and this goes through the program one line at a time. So I click on that, and it's not going to show anything just yet. It's just showing the pre-code. But now you can see when I click on it again, I have a gray box. And this is the box actually from line 1. This is an important idea on using the box command. The first two numbers are the X values. So it starts at an X value of 10. There's 10, 20, 30. And it ends at an X value of 30. In the y-axis direction, it starts at a value of -5. You can see it's halfway between the two lines below the x-axis. That's -5. And it ends at +5 on the y-axis. So it's created that box. The next step is that it's going to rotate it. And now you can see it's rotated at 30 degrees from 0 along the direction of the x-axis. And finally, it gives it a color. And then after it displays it, you'll see the box flash, and it stopped. This is a good example of seeing what each line does in a fairly complex procedure. So I'm going to go back to the webinar. The next step is that now that we've created these three objects, we're going to form a union, and you'll be familiar with this from working in any kind of documents where you use a group command to group items together, and then you can act on them as a whole. So in this case, it's not going to look any different, but it's creating a brand new object called RD, which is formed by the union of RS, RR, and S. So that's our outer ring, our socket, and our spar. All right, now we're going to work with this new object RD, and we're going to work on some geometric transformations. In this case, it's a translation, and we're moving it 26 units in the X direction and 26 units in the Y direction. And it's written as move RD, the name of the object, 26, 26. Very simple. Oh, this is the fun part. And this is one of those commands that is valuable as a generalization. Any 2D object can be converted to 3D by adding the third dimension. And we might know this as a thickness or a height. And this also makes it 3D printable. So when they start making their own objects, they can make something that's flat. They use the prism command to give it a third dimension, and voila, they can now print it out as a 3D object. So you can see I've tilted the plane here, and you can see that it's 3D. All right, we're going to do some more geometric transformations. In this case, we are doing a reflection about the y-axis. And that's a true mirror command. And then we do it one more time. We mirror both of these objects across the x-axis. It's starting to look like the drone frame. Of course, we have 4 of these just sitting in outer space, and we now need to connect them up. We do this by creating another ring, and we're also creating our first true 3D object, which is a cylinder. And again, this is exactly how it works in math. The kids will learn that you make a cylinder by multiplying the radius and the height. And there it is. There's a radius of 18 and a height of 2. So again, we're working on a prototype design. Why is the height only 2 millimeters instead of 5? Well, the answer is you're going to fit your controller on that platform and it helps keep it in place. But again, this is a question that can be used as a discussion point. Okay, the last thing we're building is a little triangle that just indicates the direction of flight. And this is another piece of geometry. Triangles are a little tricky because they come in all kinds of shapes with all kinds of angles. So the best way to build a triangle is to use XY coordinates. And in this case, we have one that's 35 and minus 9.5 in the Y. We have one that's 45 and 0. And we have one that's 35 and 9.5. And you can see on the command it's listed as a set of points. Once they are finished with that, they get to download the STL file. This is the printable file for 3D printing. And they can personalize the drone. So you'll get a link to the actual code. And if they want to, they can choose their letters. And the letters that we chose, of course, is NCL for NCLab, but they could choose their name. If they're really ambitious, they can scale the letters. So let's say they wanted to print out, I don't know, Jeff, Jeff, which would be 4 letters. Then they'd have to make them a bit smaller to fit on the platform, and they may need to move them around. So this is where they can really play with some coding. You can change the main code, but at your own risk. Really, if you want to introduce them to a bit of coding, they can just start with the letters for now and leave the main part of the code alone. Okay, so now talking about building and flying the drone, and this is a list of parts. I'm going to put in a spreadsheet on community that will give you a little more information. You don't necessarily have to use these parts. These happen to be the ones we used. Oops, wrong way. And here's a picture of them. So we're using Spintech motors. They are very fast. One thing you should know about brush motors is they burn out quite quickly. This is just the nature of the beast. It doesn't matter who you buy them from. So be prepared to replace motors if you use these extensively. The batteries we use are from a company called Tattoo. Again, you can buy them from anyone. They're lithium polymer batteries. This is the control board from Blade. This is a charger that you can plug into your USB port to charge the batteries, and this is a pack of propellers or blades. Okay, important to know about the motors. You're going to see this over and over again. Drones work by a combination of counterclockwise and clockwise motors. And the motors are color-coded. So you'll see that the counterclockwise motors have white and black leads, and they have a black end cap. And the clockwise motors have red and blue leads and a green end cap. And different brands may have different color combinations. Same thing with the propellers, and kids get this right away. They will need 2 counterclockwise propellers and 2 clockwise, and all you have to do is kind of push on it with your finger and you'll see the direction of rotation. The batteries we use are from Tattoo. Just a warning, these batteries only last a couple of minutes of flight time, so it's nice to have one on the charger while you're using one on the drone. This particular charger plugs right into your USB port. And just about lithium polymer batteries, they're relatively safe, but you do want to keep them away from heat and fire. If they look like they have swollen at all, they're not nice, neat rectangle here, they're probably bad. You can download MSDS sheets from the internet on any product. And it's a good idea to go over the safety data with your students or your club members. Okay, the control unit itself is just this little board, and one thing that's important is there is an arrow on it, and this needs to face forward when you put it on the frame. This little copper wire here is an antenna, and then on the back side of the board you're going to be plugging in the motors, and this is how the pattern lays out. You got counterclockwise, clockwise, clockwise, and counterclockwise, and then there's the lead that's going to go to the battery. Okay, so now we have our nice frame that's been printed out, and we're starting to put this together. And now we're looking underneath the board, and you can see these are where the mini Molex connectors go in for each of these motors. And I tried to enlarge this. It's very precise how you put it in. If it doesn't fit, you're forcing it backwards. Be very careful with that. It's got a specific cutout, and just make sure it matches. One thing that's very handy is that you have a little lip on them, and you can grab this when you're putting them in and out. It allows you to do that without forcing. So be aware that if you've got fingernails, it's great. The fingernails will fit exactly underneath. Okay, so I think the most tricky part is getting those motors into those sockets. And you can see unfortunately I didn't have a way to hold the camera with my teeth, but this is step one. You want to kind of really push a little bit against that opening, and it opens up the springiness, and then you can grasp the body of the motor and push it in with the other hand. As long as you get it in a little bit, then you'll be able to get it in the rest of the way. One thing to be careful about is try not to pinch those leads. They are pretty delicate, and it's very easy to just simply cut them right off. All right, so attaching the propellers, once you have the motors inserted into the frame, then you simply just push them on the pin of the motor, and it's just a gentle press. You don't have to force them on. Chances if you're forcing them on, it means that the propeller mold probably wasn't great. Okay, then I would suggest go ahead and secure them with rubber bands first. You can also, once you're really happy with how this is put together, tape the control board onto the frame with some double-sided tape. Just thin double-sided tape is fine. It'll keep it secure. The drones fly best when that board is lying really flat on the frame. Finally, you go ahead and slip that battery under the bands, your charged battery, and plug it in, and you'll see it start to light up. You have two white lights that are the forward direction and two red lights that are the rear. Interestingly, not all drones follow the same rules, but in this case, that's how the lights work. Okay, you'll need a controller to fly it, and just some brief notes on the controls. You may need to bind it. On the back of the controller are instructions. They work. I've done this many times. You disconnect the battery, plug it in, give it 5 seconds, and then when you turn on your transmitter, you push in the left throttle stick straight down and turn on the controller, and then release the stick and move it right down to the bottom, this left throttle stick. That's your safe off position. If this starts flying like crazy out of control, just flip this down to the bottom. It'll drop like a stone. This is your gas, basically. So if this is sort of step one for safety, is get that down to the bottom and it'll be fine. Your left controller controls thrust and yaw. Your right controller controls pitch and roll. Thrust, you can think of it as gas. And here's a little diagram that explains how roll, pitch, and yaw work on X, Y, and Z axes. And this takes a little practice to get the hang of. But really, it's pretty safe. Okay, I'm going to show you the video of our first flight. We were pretty excited about it when we first built this. So I'm going to go to the YouTube video and just show that briefly. It's just a real quick one. This is down in the maker space at the Innovation Center. We just finished printing the frame and putting the motors in. And fortunately, my friend Ben is a drone hobbyist, and he actually knew how to fly this thing. Okay, that's it. So, yes, you can fly them indoors. If you fly them outdoors, try and pick a day that's not too windy in an open space where you won't interfere with other activities. These are totally safe to fly indoors, though, and they're not communicating with anything in the outside world. When you get into more sophisticated drones, some of them do communicate and send their GPS coordinates because they need to stay out of airspaces, but they're basically a toy. You can carry these on an airplane too. All right, so I already showed you the printables and the lesson plans. You have note takers and reflection worksheets and posters. And in the lesson plans as well, there are applications in engineering, math, and science that can be used for project ideas. Okay, so in project-based learning, let me see if I can blow that up here so you can see it better. There are all kinds of ways you can apply what you've learned. They can write an essay, they can make a poster, they can present it dramatically, they can do demonstrations in labs, they can produce videos. They can go in and start customizing the design. Now, they may want to get into the 3D modeling course a little bit so they know what they're doing. But these are some ideas on what purpose you would use or how you would design for a purpose. You can study physics and math. You can study the physics of flight. You can optimize geometry. There's your math skill. You can use rotation to control direction. This is how drones work. And I've gone on about counterclockwise and clockwise, but they may be interested in how you model airflow. They can get into just flying a drone. There's lots of great YouTube videos that teach you how to fly them. And then there are some citizenship concerns. What are the regulations? Think about privacy, about sharing airspace, use in military operations, safety issues. Okay, a camp suggestion. If you want to do multiple sessions and bring in 3D modeling, this is a great cap to Unit 1. You can have the posters up, explore 3D modeling app on the desktop. There's always a default program on the apps. You can then start on working on Unit 1. I always like to go back and forth between computer work and offline work. It's great to take a break. You can play with 10-gram puzzles or Tetris games. You can get models of 3D shapes and so forth. Go back to Unit 1. Then it's fun to build just paper models. It gives you an understanding of the advantages and disadvantages of using a computer to build a model. Finish Unit 1, and then to wrap up, go into the tutorial. If they do it after doing these things, I think they get more out of the tutorial. Or you can flip it. You can do the tutorial first as an introduction to 3D modeling, and then, of course, fly the drone and share out reflections. I'm going to flip back to this in a second. I just want to remind you to join the community. We have posted everything from webinar 1 there, and we'll post all the materials for webinar 2 after this webinar. Okay, so any questions? I'm going to unmute you so we can talk. So, questions. What age That's a good question. We generally recommend that the students who do 3D modeling are middle school level because this marries well with the geometry they're starting to learn. They may have difficulty grasping those concepts beforehand. That being said, I used this with my fourth graders when I was teaching, and their favorite part of NCLab was 3D modeling. Okay, options for printing the drones if you don't have an on-site 3D printer. The nice thing about STL files is you can send them to someone. So you can send them to another library that does have a 3D printer. You may want to contact your local college or university if you want to do it for, sometimes they'll partner with the libraries for free to do these things. There are services, paid services, that will print as well. Any other questions? Okay, how much does it cost? Good question. The parts that we used, it works out to about $56 per drone. So it's not cheap. If you can buy really cheap drones at Walmart now for about 20 bucks. But as my grandson found out, his nice drone he got for Christmas, once the motors burn out, it's really hard to get at them to replace them. And they use the same, generally they use the same brush motors that don't last very long. I think of this really as an engineering project as opposed to a cheap way to build a drone. If you have the budget for it to get more than one kit, I would suggest assigning them to a group. Kids are often very happy just getting to play with one drone for the whole club. But yes, I would recommend getting extra motors. They're the ones that go the quickest. And it makes a big difference. Man, you redo a drone with fresh motors and off it goes. It goes like crazy. So yeah, motors and batteries is where you want to get spare parts. I will be posting the spreadsheet with the complete breakdown on the costs. All right, well, thank you so much for putting up with the technical difficulties at the beginning of the session, and I hope you guys were able to hear this clearly. I will be uploading the slideshow and a copy of the webinar, and feel free to use it for trainings or for review, or if you want to use some pieces with your club participants, that's fine as well. Our next webinar is going to be on the student management system, and we've actually just put in some new changes that are going to really help the librarians because you'll be able to add your own admins, which is nice. And I look forward to seeing you then.